Next is another example for the FET amplifier design. This circuit is a self-bias configuration with capacitor bypass. Okay, do you remember to draw AC circuit for this circuit? Okay, remember that this capacitor should be shortened here. Okay, because when it is short here, so it become bypass the RS, and we will eliminate the RS. Okay, so the question is, given the gain of 8 and VGSQ equal 1/4 VP. So if we compare with the previous example, now we get another information, which is VGSQ. So you don't have to find the VGSQ in the DC analysis. You just get this value and multiply with 1/4, then you get the VGSQ. So the question is, get RD and RS. So we have two here, RD and RS. Okay, if we see in this circuit, in the DC analysis, the capacitor here will be open circuit. When here is open circuit, so we have RS. So on that time, we can calculate the value for RS. However, during the AC, the RS is eliminated. So means that you need to find the RS during the DC, or another way, you can get from the RD first, then find the RS. Then we calculate the VGSQ here. So we get directly from the VP, multiply with 1/4, then we get negative 1 volt. Next, we calculate the GM and RD. So insert VGSQ. So VGSQ in this equation. Okay, we get GMO first here. GMO, we get 5 millisiemens. Okay, and then insert VGSQ inside this. So we get GM equal 3.75 millisiemens. Then for the RD, 1/20 micro, we get 50 kilo ohms. Okay, now you draw the AC circuit for the self-bias bypass. Remember that the capacitor is short, so the current flow from the S terminal to the ground directly, so that the RS is actually eliminated from the circuit. So there is no RS here. Okay, no RS, and this circuit is actually similar with the fixed bias. Okay, in this case, so the analysis is similar with the fixed bias, and we get here, we see VS equal to 0, VGS equal to VG. Okay, VGS here, VGS will equal to VG, and VG equal to Vin. So because of the VGS here, we substitute the VGS become Vin. So GM VGS equal to GM Vin. Now from the question, the AV is given. Okay, AV is given. So we use the AV equation to determine the RD. Okay, so we do it step by step. To get voltage gain, V out divided by V in. V out equal to negative GM VGS multiply with RD parallel with RD, small RD. Then the V in equal to VGS. so we can cancel it. So we get negative GM RD parallel with RD here. Okay, then insert the AV negative 8 and the GM here negative 3.75 milli, and also the RD here 50k. Then we solve this equation, we get RD equal to 2.23 kilo ohm. So this 2.23 is not the final value. You have to check again with the standard value resistor. So the nearest value is 2.2 kilo ohm. Next, to find the RS. Okay. During the application AC analysis, the RS has been bypassed by CS. Hence, the value of RS cannot be determined in AC analysis. However, it can be determined when applying the DC analysis. So, we go back with the Shockley equation, where the drain current ID equal to IS. So, here we calculate the ID. Okay, VGSQ we already calculate previously. We get negative 1. IDSS is 10 milli and VP is negative 4. So ID equal to 5.63 milliampere. And now we know that from the VGS, okay, from the VGS equation is VG minus VS. Okay, now we want to find VS. Because why VS? Because we know that the IS current is equal to the ID, and then we can get the RS directly from this equation. Okay, so this IS is equal to ID. Okay, so we use from the VGS here, VGS equal to VG minus VS. So we know that VG equal to 0, then VS is negative VS. So now the negative VS is equal to negative VGS. So it becomes negative 1 here. So we get 1 for the VS, the value of VS. Okay, remember that VS is not 0 because we have RS there. Okay, so from this equation, IS equal to VS over RS. Then we get RS equal to VS divided by IS. So the value of RS can be obtained by substitute equation 1, the previous equation. So we get this RS equal to 1 over 5.63 milliampere. And finally we get 177.62 ohm for the RS. And this is not the final value. You need to compare, or you need to find the nearest value in the standard value table, and we get 180 ohm for the final value.